jump into it. Okay. Luckily, there's not much I wanted to show you on the calculator in the first part, so having technical difficulties, but I'll worry about it at the break. Let's just actually get into some material. We are going to now, well, I think we started a little bit, but we're going to continue focusing on applications of the derivative. That brings us to 2.7. We'll talk about marginal cost. And rates of change. So now you pretty much know all the techniques of derivatives that we're going to do. So now we're just going to be applying it to different kinds of problems. So one important application of derivatives is called marginal analysis. And we're focusing on cost here, but let's just actually talk about what this actually means. So definition, if f of x is a function, then its marginal function is, and it turns out it's actually just the derivative, if it exists, right? So there are some contexts in which the derivative is considered a marginal function. And so let's actually talk about what that is, and then we'll talk about how to actually use this information. So suppose we have c of x, and this is the cost function, cost to produce x units. Okay. Then, if you look at the derivative of this function, that will just be the limit as h approaches 0 of c of x plus h minus c of x all over h. And remember what the limit is trying to do? It's just trying to let h get closer and closer to 0. So what we can say here is this is pretty much going to be the same as what the difference quotient gives us without the limit, just as we consider when h is close to 0. So the closer we are to 0, the more these two numbers will be looking alike. So our derivative can be considered the difference quotient, that expression when we're close to 0. Now, here's where the marginal stuff comes in. And so in some context, pretty much we're going to give h a value. H equals 1 can be considered small, as in close to 0. So we're really talking about when our function is trying to measure something massive here. So we're talking about a company that produces a lot of products. So we're talking about like iPhones, right? Millions of iPhones being produced per year. When you look at one iPhone compared to millions of iPhones, it's kind of like nothing, right? One iPhone is nothing compared to the amount of things that we're pumping through the system. So there are times when one unit is considered so small that it might as well be 0 in some context. And so we can think of C prime as the following. Just go to this expression and plug in 1 for h. And so the C prime of x will be approximately equal to C of x plus 1 minus C of x. And this is just plugging in h equals 1 in the above. And now that equation is why we can think of it as a marginal function. Now, what do you think that expression represents, the one on the right side? I were to ask you, what is c of x plus 1 minus c of x? What do you think it would tell you? What information do you get from that expression? How do you describe it in words? What do you think it tells you about? Yeah?
Would it be, what would the cost be plus one more item produced?
Well, that would be this. This is the cost if we're producing one more item. But what does it mean to subtract that? Huh? So this is the cost to produce x items. This will be the cost to produce x plus 1 items. So if I subtract them, what I'm doing is I'm just finding the extra cost, right? The additional cost to make one more thing. So this is the additional cost to produce one more item after x have been produced. So that's how we can do this expression. And then the derivative is actually an approximation for this, i.e. c prime of x can approximate this value. It's approximately the additional cost to produce one more. And so when a function is used in this way, we talk about it as a marginal function because it's telling you what's happening at our margins. At the outer edge of production, after we've produced a lot of stuff, then we're like, what if we kind of push the margins a little bit? What if we went one step further, right? So when you're kind of considering that notion, right, you're trying to judge what would happen if you just push the margins a little bit more than they currently are. The derivative is actually a good approximation of that. So maybe, okay, your cost function is doing its thing, blah, 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 and you have rising cost the more products you're producing. So you're at some point, right? So now you're at some point, and you know currently you have X products being produced, and you want to say, should we keep going? How is the situation going to look if we push this a little bit further? So basically what you do is you don't know what's going to come, and so you create a tangent line. And we spoke about this idea before when we spoke about high frequency trading and stuff like that. To sort of imagine what would it be like if you were one step ahead of where you currently are, right? So that's the kind of idea, right? So this is what's happening at the margins, and therefore it's called a marginal function. It's telling us what's happening at the edge, at the margin of what we're doing, okay? And so you can kind of use a derivative to do this, much like in when we're doing linear approximation stuff. So, and in this context, it's called marginal functions. And so, let me just say, so C prime can tell us what happens at the margins if we were to go one step further. Hence, C prime is called marginal cost. And pretty much anytime you hear someone refer to the derivative in terms of as a marginal function, it's usually going to be in a finance/economics context. Because they're always imagining something that's having some large production line, where the point where one thing can be considered small. And there are not many mathematical contexts where you consider the number 1 as a very small number. Right? When it comes to limits, for example, 1 is huge. You're 1 unit away, that's far, right? You want to really inch close to something. But in this case, 1 more is pretty much nothing. And so we can talk about what's happening at the margins. So that's what this function is kind of for. So when for those of you who are studying economics and you might just study marginal functions, this is why you would study them, this is why you're going to use them. You're always trying to predict what's going to happen if you push the envelope a little further. And so, and And this, of course, is going to be, like I gave you the definition before, it can apply to any function really. So someone can ask you about marginal profit, marginal revenue, marginal this, marginal that. All it means is they're thinking of, they want you to find the derivative, and they want you to think of it as something that will predict what will happen if you go one step further. Right? So it's a certain mindset. And so let's actually do some examples so you can see how this would look. So there are usually a couple problems like this on a final. So you should expect 1 to 2 of them. And usually I'm going to go through examples where they have several parts, but usually they'll ask about one thing, right? But I want to show you several different situations that you should be able to talk about. So let's look at example 1 here. So example 1 says, suppose the cost of producing X glow-in-the-dark boxer shorts is, so we have a cost function here. And remember, cost functions are always given. It's not something you can mathematically figure out, like sit in your basement and derive a cost function. Depends on the situation, depends on the business that's being run, how many employees they have, how much it's costing them in rent, how much is, they have to pay for permits, from the government or whatever, right? So cost isn't something you can figure out. It's always going to be given to you. So let's say you are given that this is the cost function for a certain glow-in-the-dark boxer shorts business, and they might say, A, what is the additional cost to raise the production level from 10 to 11? So we want additional cost. To go from 10 to 11. Now, this one, I'm asking for the actual additional cost. Okay. So this isn't really having to do with derivatives. I actually just want to compare this to derivatives. And so what you would do is the additional cost is going to be, find how much it costs you to make the 11 things, and subtract what it cost you to make the previous 10 things. And that will be the additional cost to make that one more product. And so that would be 2 times 11 squared plus 3 times 11 minus 2 times 10 squared plus 3 times 10. This would be 2 times 121 plus 33 minus 230. Right, that's 200 plus 30. And this would be 242 plus 33 minus 230. 242 minus 230. That's going to be what, 12 plus 33? That's 45. So it'll cost you $45 to make one more boxer shorts. Those are some expensive boxer shorts, but that's just for a comparison. Now, in part B, it says, compute the marginal cost at 10. Now, I mean, 10 units is nothing, right? So the approximation here isn't going to be that great, but it should just be illustrative of how something like this would work. And so part B says, find the marginal cost at 10. So you just have to remember, whenever they say marginal anything, they mean the derivative of the thing. Right? So right now, that's another synonym. So we know whenever you see slope, you should be thinking about derivative. Whenever you see rate of change, you should be thinking about derivative. See instantaneous rate of change, you should be thinking about derivative. If anyone mentions a tangent line, you should be thinking about derivative. There are a bunch of phrases that should shout at you, derivative. This is another one now. Marginal is something that should shout at you. Derivative, you should be taking a derivative somewhere. So if they ask for marginal cost, you should be taking the derivative of the cost function, and you're going to plug in the number 10, right? So this is asking for the derivative of the cost function evaluated at 10. So first, let's find the derivative of the cost. So we're going to differentiate this, not a difficult thing to do, that's just the power rule. in 4x plus 3. And so now that would mean at 10, this will be 4 times 10 plus 3. And that's 43. Now, it's not off by that much. You're off by $2, which, I mean, depending on how many things you're producing, being off by $2 per unit could be a big deal. But, I mean, we're talking about 10 units here. It's not going to be that close of an approximation, but it's actually pretty good, right? So, pretty much, if this were to continue in the future, this would be what the actual cost is, and this would be what someone would guess the cost would be if they didn't have that future knowledge, right? So, I mean, it's not off by that far, but we're also not having a lot of units to work with here, and pretty much a quadratic function is way too simple. It doesn't increase that fast, and so the approximation is not going to be off. But that's pretty good, I think, for this silly example. And the thing is, in general, and I also did mention this with the high frequency trading example that I mentioned a while ago, is that sometimes if you're wrong by a little bit, it's okay. If you're right with most of your answer, that usually works out for you. And especially in business, it's often good. It's better to make a good decision quickly than to make a perfect decision later. And that's what you should notice here. So this is the actual answer, but if you had this guess, it would be a good thing. And if you could act on this guess quicker than you can act on that one, in general, you would be in a better position. So, yeah, turns out that the derivative at the point is kind of an approximation to the one-step difference. So that's why marginal cost functions are used in an economics context. But for us, just remember that marginal means derivative. Now they can throw all sorts of context at you and they can make it even a little bit more complicated. So let's look at example 2 for a little more complicated example. Are there any questions so far on the idea of marginal cost? So you just need to know marginal means derivative, and in the case of economics and finance, we can use its value at that point to approximate the additional difference between that point and the next point. And this is useful because you might not always know, you might not have a formula to predict what's going to happen in the future. It's really going to be a guess, but it turns out that things don't change that much from one unit to the next. And so this little bit of predictive power can be very powerful. Okay. So I'm going to put an example. I want you guys to kind of tell me how you work through this one. So suppose you're given a demand function. So you do your research, you figure out a demand function for a certain product, you find that that's going to be it. A. Find marginal revenue. B. What's the marginal revenue at 10? C. Suppose I gave you that the cost function for this product is x squared plus 2x. What is the marginal profit? What is the marginal profit when x equals 100? I also wanted the marginal revenue. I want you to interpret your answer to D. And then answer the question, is it worth producing one more? Okay, so something like E wouldn't be asked on a final, but it's just something I want to get you guys to think about how this thing would apply so that a word problem in the final won't confuse you because you fully understand what it is you're looking for here. So I just want to make sure that you actually know how you're thinking about it. Once you know that, it's harder for word problems to confuse you. I didn't know what they were asking. Well, it means that you don't really know how to interpret the calculations you're making. You have no idea what you're calculating. You just know that, oh, I think I'm supposed to do this. You should know what you're supposed to be calculating, and that will help you to answer problems. So, okay, if someone gives me a demand function, how would I find the marginal revenue? Yeah?
Well, find the derivative of that function.
Sure, to find the marginal revenue, you have to find the derivative of revenue, so yes, that's good. So, then the question is, how do we find the revenue? Times it by x. So remember what the demand function is whenever you see that shows up. Remember, that's a function that describes the price people are willing to pay you for your product, right? So if you produce X units, the price you can charge that people will pay is going to be 25 over radical x, right? So say in your production, you produce 100 products. You can expect to sell them at $2.50. That's what this function is going to tell you. So the demand function gives you the price consumers are willing to pay. You need to remember that. We did talk about that, but just to remind you, price consumers are willing to pay. So whenever you say a demand function, that's what you're thinking about. So now if you know that's the price they're willing to pay, and how do you find revenue? Well, revenue is always the price per unit times the number of units you're selling, right? So you're just going to take the price per unit, which is this expression, and you're going to multiply by the number of units, which is x itself. And so you should remember that revenue, and this is a formula we discussed a while ago. I don't remember if it was last year. It's just x times the demand function. So that's just going to be x times 25 over radical x. And so that's going to be 25 radical x. Now that's your revenue function. But they asked us for marginal revenue, so that means we're going to differentiate this. What is the derivative of 25 radical x? Come in. What's the derivative of radical x? Well, the derivative of it. We'll find derivative.
You do 25x to the half, and then you do 25x. Is it?
Is it 25 over 2x squared?
No.
Is it, so you make it 25x to the half and then
Yeah.
multiply the half with the 25 and then minus the 1.
Yeah, so what would you get?
So
So you're thinking of this as 25
so it's
x to the 1/2, so that would be,
17.5. Wait, what?
So it'd be
so you bring down the
25
half,
over 25,
and then
A negative 1/2.
negative 1/2,
so it'd be
so that is, it's 25 over 2 radical x. Remember, derivative of radical x is 1 over 2 radical x. That's one of those things you should know by heart. You shouldn't even have to go through this. I mean, if you have to, you do it. But radical x is something you should just know that's what it is. It's like, if I ask you, what does y equals x squared look like? You shouldn't have to like be plotting points. You should just know it looks like that passing through the order. This is such a function. See radical x show up, you should know derivative is 1 over 2 radical x. And if there's a constant in front, it just stays there. So that is the marginal function. So r prime equals 25 over 2 radical x. That is the marginal revenue. Okay, B. What is the marginal revenue at x equals 100? Well, that just means you plug in 100. And so that will be 25 over 2 times radical of 100. And that's going to be 25 over 20 And that is, of course, it's going to be 1.25, something like that. Right, because 5 into this goes 4, 5 into that goes 5, that's 1 1/4, 1.25 would be the marginal revenue. Yeah.
For the marginal revenue, if you got 12.5 over x squared, I mean x radical x, that would be the same, right?
Yeah, you can say 2 into this goes 12.5. But it would be weird to write this 12.5 over radical x. It's kind of weird to write it, but it's not wrong. Like usually when you put things in a fraction, you don't put decimals in a fraction, right? You usually want to write it such that there are whole numbers there. So 1.2, so you get 1.25. By the way, extra question, what does that mean to say the marginal function at 100 is 1.25? How do you interpret that? What does that
So
mean?
one,
So if someone tells you, at 100 products, the marginal revenue is 1.25. What are they saying to you?
After 100 products, each product is, it'll cost you $100.25.
Well, it's not cost, it's revenue.
But will, I guess it'll
You'll
be,
be,
So you'll make so it means that if you currently have 100, by producing one more, the amount of revenue you will generate is going to be $1.25. That's what they're saying, right? So remember, the marginal is just, it's approximately the additional amount that will occur by doing one more. So marginal revenue is the additional revenue you'll make by doing one more. Marginal cost is the additional cost you'll incur by doing one more. Marginal profit is how much money you'll make if you do one more. Marginal is always just an approximation for one more, the additional difference between the current level and one more. Okay, so C. Okay, so they told me a cost function. How would I find marginal profit?
subtract the cost function from the revenue function. For
So profit is equal to what?
the revenue minus cost.
Revenue minus cost. So you subtract cost from revenue. So that's how we're finding profit. Now we know that for marginal profit we need to take the derivative, but let's find the function first. And so this will be the revenue, which is this guy, 25 radical x, minus the cost function, squared plus 2x. And so this means that if I want to find the marginal profit, I just want to differentiate this. Derivative of this we already found, that's 25 over 2 radical x, minus derivative of this is 2x, derivative of this is 2. So that is the marginal profit function. D. What is the marginal profit at x equals 100? Well, now we plug in 100. And so that's going to be 25 over 2 radical 100 minus 2 times 100 plus 2. So this we saw was 1.25 minus 202. So this is minus 202. Okay, so I want you to interpret that number and then tell me, is it worth making one more unit? Right, so what would you say this means? So the interpretation here is what?
that,
You lose $200
You lose $200 in what situation?
making one
Make
more
it-
If you make one more, you're going to lose $200, right? This means we will lose, not lose, lose $200 by producing one more. So of course the answer should be no, it's not worth it. In fact, if you're losing up to $200, it's probably wasn't worth it for a while now. You probably should have stopped producing a while ago, right? Because I'm pretty sure you weren't making profit on the 99th one either, with a loss like 200. So not worth it. Right? So pretty much with some statistics in your back about like market trends and how things are working, and you're managing your price, and you have all this data you're collecting. You just have a really strong machine with a program on it that's always like constructing marginal functions to kind of see ahead of the curve, ahead of where we are, and say, should we keep going? Should we pull back? You know, what do we want to do? So marginal functions can be useful in that sense. And so, like I said, this was a lot of parts, but a question you might be asked is any one of them. So they just might say in the problem, oh, here's a demand function, and here's a cost function. Find the marginal profit at 100 units. And you would need to know that you need to find the revenue, subtract the cost. The revenue is going to be X times the demand. Then you'd have to find the derivative and plug in the number. Like you might be expected to do just part D from the original step. So what you need to remember is marginal just means derivative. And whenever they use that phrase, it's just trying to approximate what would happen if you make one more. And you should also remember the formulas for these guys that I told you about. So revenue is always X times the demand function. The demand function tells you the price that you can charge, and people will actually pay that price. Right? Charge more than that, people just won't pay it. Right? Charge less than that, you'll lose money. Kind of thing. So the demand is going to tell you how much you want to charge. Okay. That's pretty much it.
Professor?
Yeah.
To find the demand function again, that's the one that's always with the subtract?
Come again?
The demand function, that's
Well, you don't
always-
find it. It's going to be given to you as well. Because the demand, like cost, is something that depends on the situation.
Yeah, but you taught us a way how to like realize that that's the demand and that's the
Oh, demand is always a decreasing function.
decreasing, right?
So there are problems where they'll talk about both supply and demand that's in the same problem, and you should know to figure out which is which. The demand is always going to be decreasing,
Okay.
and the supply is always increasing. So in that situation, you know that this is the case. So demand is always moving down, and supply is always moving up. But you'll need to know that in questions where they mention both. But in any question where they just mention the demand alone, take that as your price.
Okay.
Could you find out, given that, E, could you find out when they should stop making more products? Like when they reach the pinnacle?
Yeah. So you can pretty much go here to the marginal profit and set that equal to 0,
Okay.
right?
Yeah.
So you can find the number of products that would make the marginal profit 0, and that means at that point,
Stop.
one more step means you're making no money. You should have stopped at that point.
Okay.
So you could have set this equal to 0 and solve for x, and that would tell you where they should have stopped. But yeah, here they should have probably stopped a while ago.
Oh, yeah.
Okay, so another application here. More applications. So kind of going away from marginal function, this is one application. You might have 1 or 2 problems on this. You might have one like in both the written section and the other section, because sometimes they'll have prices which you have, working with decimals, they'll expect you to use your calculator. More applications is this one is more physicsy kind of application. There's motion. Right? And this is when you're considering something like the position, the speed, and the acceleration of some object. Which we kind of looked at that when we were talking about derivatives, right? We figured out that we could use slope to measure speed by we were tracking some object moving at a certain speed. So what you should know is that S of t, let's say you have some function, usually called S, that gives you your current position at time t. And you should realize that if you were to take the derivative of the position function, this actually gives you the velocity function. It tells you how fast that object is moving. And if you were to take the derivative of that, which is the second derivative, or the first derivative of velocity, that will give you something that we call a of t, which is called acceleration. So if you, basically if you want to move down this list, if you want to talk about position, velocity, and acceleration, if you know about position, you can differentiate to find out about velocity, you can differentiate that to find out about acceleration. So this is, where is it currently located? How fast is it moving? Is it speeding up or slowing down, right? In succession, those are the kinds of questions these guys can answer. And differentiating is what brings you down this list. So you keep taking derivatives, and you will be able to go through these functions. It's worth mentioning here, we're not going to do this, but in the next class, you're actually going to learn how to reverse differentiation. And that's called integration. That's next class. So hold on to your horses. Integration in general is harder than differentiation. Derivatives are going to be, you're going to be praying that all you get to do is derivatives once you learn about integration.
Yeah, it is.
Those can be very, they can be very tough. I'm not sure if they'll be tough in the next class, but if you're someone who has to do even more math than that, by the time you get to that class, integration is going to be like, yeah, forget it. You're really going to have your hat on really tight for that. But yeah, you should know that you can go from position to velocity to acceleration by differentiation. So that's one application. In fact, that's probably the application. When Newton was coming up with his theory of calculus, he was pretty much doing this kind of analysis on things, which is where he came up with derivatives and stuff. It was actually like tracking the planets in the solar system, and he's trying to predict orbits and stuff. So it's like, oh, the planet's moving this fast, where is it located now versus then? So he was really trying to track things. What is their position? How fast are they moving? Do the planets speed up at some point? Blah, blah, blah. So that's the kind of stuff he was considering when he invented calculus, or invented our current understanding of calculus.
So calculus ties into physics, or is that like its own thing? Like, do they use like calculus in like physics?
Oh yeah, for sure.
Velocity and all that?
Calculus is the mathematics of natural sciences. That's basically where it's going to be used. So physics, biology, chemistry, there's calculus underneath all of that. Oh, that reminds me. Now I know biology students usually don't think of what they're doing as very mathematical, but you can't do anything in science without math. Someone somewhere had to do math.
They go hand in hand.
And some people just never realize it's happening, but it's just because they're unaware. I was listening to a podcast the other day about how calculus is used in real life and stuff like that, and you'd be surprised. Like, even what we know about things like, you never think about it, like HIV treatment, like calculus is what figured that out, right? Because like when the virus transitioned from HIV to AIDS, it did it in a weird way that no one could figure out why it does that, or why does it go dormant for 10 years? What is it doing? Was it attacking your body? Was it not attacking your body? Someone used calculus to figure out the answer to that, and then they could invent the drugs to fix the problem, right? So once you're doing science, calculus is going to be important. And yeah, Newton was interested in physics most of all, so he was studying physical objects, but he couldn't describe it without the math. You can't do anything without the math. So he cares about this physical object. He had to figure out what math can describe that object. You can't get anywhere otherwise.
Could you say the same thing about like math can't be used without science? Like, is it like that? Is it vice versa? Or
Oh,
just,
no, it's not vice versa.
just science can't be?
Yeah. Math is its own thing, it turns out. In fact, in many ways, math precedes science. There are a lot of times math people just go on and they just push math as far as they can for no applicable reason. They're like, no one's ever going to use this in real life. How many people are going to have an infinite number of things lying around? Let's talk about infinity, right? And it turns out that, years down the road, sometimes centuries, now we have these complex problems in the world now, and we're like, hey, like 200 years ago, someone did this in mathematics. I think it applies now, right? So you'd be surprised. The math is always going to be ahead of the curve, and you can't do anything without it. Yeah.
You see the movie Behind the Figures?
I did not. I've heard of it, but I wanted to see it.
This one part of it was it's a very smart woman. They couldn't figure out where the like the holding chamber for the astronaut, where it would land when it comes back down.
Yeah.
And they couldn't figure out because the math was never adding up. And it always like they would get one number but it would end up somewhere else.
Yeah.
So she looked back to like some like ancient Jews who used a different formula.
Yeah.
Like work perfectly with like what they were trying to do.
Yeah.
It's pretty cool how it ties together.
Yeah, stuff like that happens all the time. We're going to learn about matrices soon. We're not going to go that deep into it, but you can think about why Google is Google is because someone thought of a really creative way to use matrices. That's pretty much it, right? I don't know if you guys remember, you know, when I was younger, there were tons of search engines. There was no one like search engine. You know, you had a bunch of things. Like you had Lycos, you had Alta Vista, you had Web Crawler. You had a bunch of search engines. Everyone kind of used whatever. Google looked at a different way to do search by relevance, and it was pretty much they applied matrices in a creative way. Hey, remember that thing we learned back in college, linear algebra class? Yeah? You know that Markov chains thing? Yeah? I think we can use it to sort websites. Now Google is synonymous with search. People say, just Google it. Why? Because these guys use matrices. Right? So sometimes the math is going to be ahead of what you're doing. But you can't do anything without the math. Physics, it kind of, as Newton wrote it, they went hand in hand though. He was studying the physical objects before he figured out the math. And he had to figure out the math to be able to predict what the objects would do. Yeah, in terms of this, you don't have to know much about it now. Just know that you can travel through those functions in this way. We'll just do a word problem and move on. We're going to do example 3 in this handout. It's not a shameless plug or anything. I'm not saying everyone should be a mathematician. I'm not that extreme, but you should recognize it's important. And you know, if you're ever think that you could potentially be in a position to like invent something, math is something you're going to want to be good at. So here's a problem. And again, I gave you many examples of possibilities, things that they could ask for. But you know, they'll probably ask for one of these things if a problem like this shows up. Okay, example 3. A group of angry calculus students allegedly throw Jhevon off a cliff. Okay, if Jhevon's position above the ground in feet after t seconds is given by this function. So this is the position function, Jhevon's position. Minus 16t squared plus 16t plus 32. By the way, yeah, in physics 1, all those equations you got for equations of motion, you know, position is at squared plus v naught t plus s naught. All that is calculus, they used to figure that out. Okay, so that's the position function. And so we have a bunch of questions now. How tall is the cliff? V. What is the initial velocity? Right, so how fast did they throw this guy off the cliff? C. When is Jhevon 32 feet above ground? C, D. When will Jhevon hit the ground? How fast will he hit the ground? So what speed will he be moving when he hits the ground? This is another interpretation. Interpret the signs. And again, the interpretation is just so that you don't get confused by word problems. You actually know what they mean. So they could ask you a certain word problem in a specific way, and they might be referring to something specific. You need to know what you're talking about. Okay? So that's the position function, A. How would you say how tall is the cliff? So this is t seconds after the throwing happens. Okay? So how tall would the cliff be?
Really solving for y. Well, you know the ST.
Sure, that's the y, but when would you solve for it?
For what? Now? For the cliff.
Yeah.
That's for the position.
Yes, but
Okay.
how?
So,
You're solving position,
we
which
should just
word?
do a factor of the 16 and then get the factors of the negative 1, 2.
Are you setting this equal to 0?
Yeah. I'll do
Why
that.
would you do that?
I wasn't trying to solve for y. No?
Yes, but why would you set it equal to 0? If I were to tell you position equals 0, what would I be saying?
Then it's like on the ground.
That's on the ground. Okay, so that we have the cliff here, that's the cliff, right? So this is the cliff, right? The height is what they're asking us. We don't know, but I do know the ground, that's position 0. So the only way I'd set that equal to 0, position 0, right? That's when he's 0 feet above the ground. So if they're asking me for the cliff, I wouldn't set the position function equal to 0. That's finding when he's on the ground. Right? So in the beginning, he threw him off this cliff, and he eventually hits position 0. But what position is he in the beginning?
Should you use vertex?
No, that probably also won't be, because what if they threw him up? Then the vertex is going to be here, which is higher than the cliff.
So something like f of x plus h minus f of x, so that you're getting the difference in between space. So it's a,
That's too complicated. You guys are actually thinking way too complicated. The cliff happens, he's on the cliff in the beginning, right? Just before they throw him off.
32.
Yeah, I was thinking too.
Yeah, that's it.
It's
It's
zero.
32. The cliff just means the initial position. That's where the thing starts. That just means plug in time equals 0. This is in the beginning, right? In the beginning, time equals 0. T equals after some time, he will hit the
We're
ground, but we
learning
don't know what
physics
that is.
now.
What?
We're learning physics.
We have calculus.
Oh, no, we're learning like the first lecture in physics.
Physics is always
The first
16
lecture.
t squared. I'm tired of like every time we read in physics, it's always these 16 t
Yes,
squared.
but do you know why?
No.
There's a reason why it's always 16.
I don't
Because
remember.
you start with acceleration due to gravity, which is 32 feet per second squared, and you actually reverse the derivative twice. And by doing that, you would get to 16. So remember, if you differentiate the t, if you have minus 16t squared, differentiate that, you would get minus 32t. Differentiate that, you get minus 32. Turns out that's the acceleration due to gravity. And so if you think of, oh, gravity's pulling you down at 32 feet per second squared, what you do is you reverse the derivative
That's why
twice,
the AP
and you'll
physics-
always get a 16.
It's all the questions is always 16 t squared. Like
Yes,
even the
because gravity is minus 32 feet per second squared. And in America we always think in feet. So if you're using meters per second squared, it wouldn't be 16. It would be 4.5 would always be the number.
physics is a struggle. It's hard.
Yeah, physics is tough. It's harder than math, I think.
It
Anyway,
is.
so initial position is what they're asking for. In the beginning, where is his position? That's just time equals 0. So this is just s of 0, which is 32. So this cliff is 32 feet high. Not super high. I don't know how much damage it would be to drop from 32 feet. But what is the initial velocity, right? So in the beginning, how fast, right? So this means like you're grabbing and you're throwing him off a cliff. Once he leaves your hand, how fast is he moving?
32.
Why would you say that?
Minus 32, right?
It would be mine.
You say that's gravity.
No, velocity.
The derivative.
You take the derivative, right? So remember, if s is position, then s prime is velocity. So if you're asked about velocity, you should be taking the derivative. So what I'm going to do here is find the velocity function. This is going to be the derivative of the position function. This is going to be the derivative of that, minus 32t plus 16. And so now initial velocity, initial just means time equals 0. Initial velocity is just the velocity at 0, which in this case is 16. So in this particular scenario, they throw him off at 16 feet per second. That's really fast. That's it, C. At what time is Jhevon 32 feet above the ground?
So at 1.
So 32 feet above the ground is referring to what?
Height of the
Height.
cliff.
No, like in general. Is it a position? Is it a velocity? Is it a acceleration?
Position.
It's a position, right? So they're asking, when is Jhevon in this position? And so we know how to measure a position. So this just means we want to know when is position equal to 32. So that means we want minus 16t squared plus 16t plus 32 equals 32. This means minus 16t squared plus 16t is equal to 0. You can factor out a common term. Take out negative 16t. You get t minus 1. Right? So you'll get t equals 0 or t equals 1. Right? So there are 2 times he's in that position. At 0 seconds, which is literally the height of the cliff, we already know that's the height of the cliff. But there's another time, after 1 second, right? So there's another time he hits this level, and that's when t equals 1. So obviously you kind of see what's happening here. He was thrown up off the cliff. It was actually in the position of 32 twice, in the beginning, and then 1 second later. So he's thrown up. What about E? When will he hit the ground?
When will it hit the ground? So it will be at 0 when it's at 0.
When what is at 0?
When
So when you're reading these word problems, again, you have to kind of translate it. When they say when, what are they asking?
the velocity time.
They're looking for time, right? So the time when hit the ground, how would you explain
That's
that?
the
The
velocity.
ground position.
The ground is position, and what position?
0.
Position is 0. Right? So when you read that, when will he hit the ground? What you should interpret that is, they're asking me for the time when position is 0. Okay? So this is
So you said the
when is position 0. Now we get to what you were suggesting in the beginning, right? Because this is asking when it's on the ground level. So this means we would actually solve this guy equals 0. How would you solve that?
factor.
Factor. 16 is a common term, so let's factor out minus 16. I get t squared minus t minus 2.
So it's then you this is factor.
Is that factor?
T
It's going to be 2 and 1
minus
minus 2
2 plus 1.
plus 1. So that means t equals minus 1 or t equals 2. Now obviously t equals 2 is what you're going to take because you would reject negative time. We're not in quantum physics here, right? So that means after 2 seconds. So he goes up, and after 1 second he's here. Within another second he hits the ground. So this will be a 2-second trip here.
know he's 32 above the ground. Could you have 16 feet? Like, is that a coincidence that like 2 times 16 would be 32?
No.
It's
not.
So instead of doing all the math, can you just do that? Like see from 16 how would you get to 32, which you already know, which would be 2.
The connection isn't like a multiplication. The connection is actually integration. So that's I might talk a little bit about that afterwards. So let's continue here first. How fast will he hit the ground?
That would be velocity.
That's velocity, right? So how fast is talking about velocity when ground means position is 0. And we know position is 0 at t equals 2. This means we want
2 seconds.
velocity at 2. After 2 seconds, how fast is he moving? And so we'd be able to say, we actually already found the velocity, it's here. So v of 2 is going to be minus 32 times 2
Plus 16.
plus 16.
64 plus 16. So it's 70. 64.
That's 48.
48.
Okay, so interpret the signs in B and D. What would you guess the signs mean?
B and D.
Yeah, in particular here, notice that this was a negative number. Whereas in B, the answer was a positive number. What do you think these numbers mean?
So it started at 0.
Yeah, the whole fiasco started at 0.
So
But the initial velocity was positive 16. And the velocity when he hits the ground is negative 48. How would you interpret that?
Would it slow down?
No. Speeding up or slowing down is done by acceleration. So you need to know about the acceleration because we'll talk about that. So the common interpretation here is direction, right? So positive means moving up, and negative means moving down.
So it
Right.
started up.
So this means initially when they throw him off, they threw him up, right?
And now-
Which made sense when we're drawing, after 1 second he's at the same place he was before. That means they didn't throw him like that, they threw him like that, right? So he was moving up in the beginning. And here, when you hit the ground, obviously you're moving down at that point. So
in the beginning.
there's a convention here when you're talking about motion, is that your positive and negative signs actually indicate direction when it comes to velocity. So that's how you can use derivatives. And sometimes you might need a derivative, sometimes you might need to solve an equation, but you should know when the derivative would apply. To just talk a little bit about, so let's say you have constant acceleration, a of t, let's say let's call it a, which is a constant. So one thing, if you wanted to go to velocity, you have to remember that you were actually, to get from here to there, you have to differentiate. So to go from here back here, you have to kind of do the reverse of that. So now you kind of think, what would I have to differentiate to get a constant a? Well, I'd have to get a t, right? Because if I differentiate that, it just gets the constant. Plus some constant, right? Because if there was like a plus 5 here, it would die. And so now you try to figure out what that constant is. You can use the initial velocity. V of 0 would be a times 0 plus c So this means that your c is the initial velocity, which we normally call v naught. And so you get your velocity function is at plus v naught. And then you go one step further, you go to position, and you kind of try to do the same thing. What if I want to reverse this? What would this have to come from if I were differentiating? Well, the answer is it would have to be this. Because then if I differentiate this, the 2 would die and I would get that. To get that guy, I would have to be this times t. And then there'll be some other constant here, maybe a plus 7, a plus 9, a plus 5, doesn't matter, some constant that would die. And to figure out that constant, you can use the initial position. Well, that again is going to be c, which they call s naught. And so ultimately you end up with a position function is going to be a over 2t squared plus v naught t plus s naught. And so in physics they tell you that's the formula if you want to find out a position function for something moving with constant acceleration. And it turns out now, if you plug in a equals minus 32, which is the acceleration due to gravity on Earth, this number is always going to be minus 16.
No, I've never seen that before.
Well, you didn't do calculus. Yeah, in like a physics class, this is like in chapter 1. It's always in chapter 1.
Yeah, but like,
I haven't
Like
seen it
motion.
like that, written like that. The way it's written.
Maybe they use x's or something else, but as far as I know, that's very common physics notation. You don't have to know that though, I was just asking. It's because he seems curious. Do these numbers have any connection to each other? And the answer is not really. These have nothing to do. This number here is going to be the initial position, and this number here is the initial velocity. It just so happens in this situation, they threw him off with double the speed with half the speed of this, but they didn't have to. They could have thrown him off at 7, and this would be 7. So it's the calculus that makes the connection, not really some formula like multiplying by 2. What else do we have? One last one. I think this one is actually fine. I probably even mentioned it already, but it officially comes up in your textbook at this point. And this is average rate of change. This is basically how you change on average, right? So say you're here, A and B, your function is doing something, and you want to know about, on average, how much did the function change between these 2 points. So this would be f of B, that would be f of A. And you kind of want to measure the growth from this point to that point, or maybe the decreasing, based on the average number of units between here, and of course, that's kind of just the slope. Average rate of change is the change overall. It's going to be f of B minus f of A over B minus A. So it's the difference quotient. Pretty much the difference quotient without a limit. Now, as we made these 2 points close together by taking a limit as the distance goes to 0, that gives us the derivative, and that turns this blue line into a tangent line, and that becomes the instantaneous rate of change. So this is not what we're talking about here, but just recall that the instantaneous rate of change that's just another name for derivative. But this is how something would change on average. You measure just what was the rise over the run of this thing, and that's telling you how much this is changing per unit of that thing. And that's pretty much it. I feel like we've spoken about this so much. Average rate of change. It's like, I don't know, call it f average, and that's f of b minus f of a over b minus a, and this is on the interval AB. It's measuring the slope. And these guys aren't so bad. Normally when they're asking about these guys, it's going to be a very straightforward problem. They're just going to tell you a function, and they're going to ask you what the average rate of change is on some interval. And it's not going to be worded any more confusing than that. So if a problem like this shows up, it's really a giveaway problem. Make sure you don't get it wrong. It just comes down to, can you plug into that formula curve? So here's an example, and it'll look pretty much like this whenever you're asked about it. They're going to tell you about a function. Suppose f of x equals 2 minus 3x squared. Find its average rate of change. On the interval. Now the only way this can be made complicated, it's not that complicated, is that they might write this in a different way. They might say something like, oh, for the x values between 1 and 2. Or they might say something like, from x equals 1 to x equals 2. Or something similar to that. There are ways that they can phrase things differently, but pretty much it's not going to be more complicated than that. They're just going to give you a function, ask you for the average rate of change, and they're going to indicate to you what is the x values that you're going in between, and you always think of the first number as the a and the second number as the b in that formula. So since there's not much to do here, let's just jump into it. So the average rate of change that they're looking for is going to be f of 2 minus f of 1 divided by 2 minus 1. Take that as b, that is a. F of b minus f of a over b minus a. So now, hardest thing here is to remember that what f of 2 means is to go to f of x, everywhere you see an x, you plug in a 2. Minus, in parentheses, and everywhere you see an x, you now plug in a 1. This is all over 1 in this case. And that's going to be it. So this is just going to be 2 minus 12 minus 1. So that's minus 9. And by the way, how you can interpret this number, this basically says f of x decreases, right? That's what the negative sign means. By 9 units on average over this. Right? So every time the x unit moves 1, the y value will drop by 9. That's kind of how you want to think of this. So if your average rate of change is positive, it means overall your function is increasing. Now, in between, your function could be doing whatever it wants. It could be very wavy, but it's just saying overall, between 1 and 2, it fell 9 units. So when you don't care about specifically what the function is doing, you just want to know overall what happened. Well, overall, it decreased by 9 units over this. 9 units per unit length over this interval. Any questions on this? It's just knowing if you see that average rate of change, it's talking about this formula. And this is the right endpoint, that's the left endpoint. One more application to talk about and we'll take the break afterwards. Now this one you definitely should have the handout printed out and you need to work with it all the time when you're doing your homework. Because these problems that they can be hefty to work out, but the strategy will always stay the same, and if you know the strategy, things will be fine. So this topic is called as 2.10. It's called related rates. And just the quick bullet points here. For one, related rates problems will be word problems. So let's actually talk about what they're talking about, how you recognize that this is a related rates problem that you're reading, that's a word problem. So basically the idea is if quantities are related, if two things are related, right, so you can set up an equation that connects two or more things are related. Then it turns out that their rates will be as well. Okay? So, who's that show? Some kind of demonstration going on. So if I can talk about two things that are related to each other. So let's say I'm studying chemistry and I have an equation that relates the pressure and volume of a gas. This is a relationship between those two quantities. It turns out how fast one is changing is directly connected to how fast the other one is changing as a consequence. And you can actually figure that out. We can figure out the relationship between the rates. By just differentiating the original equation. It's going to be implicit differentiation, so hopefully you remember what that means. Bullet point here is that your independent variable is always time. Here, the independent variable is always time, which is usually denoted by lowercase t. So this is a bona fide rate. We're figuring out how fast something's moving over time. Okay? So we have things that are related, and in general we're going to want to know about some rate relationship. So, and like I said, it's going to be a word problem. So let's talk about how you can recognize that you're looking at a related rates problem. How do you know? Looking at a related rates problem. So you'll see a few word problems on your final and on the next test. So you don't want to be confused and not know what method you want to use or not know what strategy you want to employ. So if you're reading something that's very wordy, how do you know if it's talking about if related rates is what you want to think of it as? Well, there are two telltale signs that says that the problem you're looking at is a related rates problem. The first thing is related things will be described, related quantities will be described. Right, which might not sound like anything particularly special. Well, every word problem is about them telling me about something that's related to something else. But what makes a difference is, and you're told the rate of change of all but one of them. So someone's going to say, hey, these two things are related, and guess what? This one is moving this fast, right? So that's how it's going to be, right? They're going to tell you about things, some relationship between two things, and then they're going to tell you how fast one of those things is moving. And then the question will be, you will then be asked, to figure out the rate of the other one. That's it. So a related rates problem, that's going to be the template. That's always how it's going to be phrased. Now specifically, it can vary widely, but when you read the problem overall, it's going to be saying something like this. These two things are related. This one is moving this fast. How fast is this one? Related rates problem. Now, once you know it's a related rates problem, you're going to follow the 6 steps in the handout. So, in the related rates handout, in a box, I described to you the method of related rates. So there are 6 steps. Here it's very wordy because I'm kind of explaining each step, why you're doing each step, what you want to accomplish in each step. But when you remember it, after reading through it once and practicing a few problems, you really want to remember the things in bold, right? You really want to have those as memory pegs in your mind. So I need to be doing this, then that, then that, then that, then that, then that, right? We'll always go through these 6 steps for any related rates problem, and this will solve any of them. So once you realize the question that you're being asked is of this form, you immediately know, oh, I should be going through this process right here. Okay? And the first part is to read the problem carefully. So not only do you want to read the problem to not only recognize it's a related rates problem, but you want to be able to pick out the particular values that are going to be important. You also want to notice if things should be positive or negative, and that comes from the idea that we looked at, that if a slope is positive, something is increasing. If a slope is negative, it's decreasing. So the word problem might describe to you something as increasing or decreasing, and you need to know in your mind, oh, certain things I should make sure they're positive, certain things I should make sure they're negative. So you're going to read the question very carefully, because all these phrases are going to be important. Increasing, decreasing. This is getting bigger, this is getting larger. This one is speeding up, that one is slowing down. Those terms are going to be very important. You're going to want to know the signs. So reading the question carefully is very important. I've made it an official step in this process. 2, when possible or necessary, you're going to draw a diagram. Now, in Math 2009, it's pretty much always going to be the case. It is very common for them to ask you something that has a direct geometric shape that's attaching to the situation. So when you draw a picture of the situation, it's going to be like a rectangle or a triangle or a circle. It's going to be some sort of geometric shape that's going to pop up, right? And so there are times when you can't draw a picture of the situation, but in this class, they're going to give you a situation where you can draw something to describe it. It would be very, very strange if they don't. I've never actually seen them do otherwise, right? So they're going to describe a situation to you, and you'd be able to draw a picture of the situation, and it's going to be some shape that you can now manipulate. What you're going to do then is you're going to label that diagram. So you're going to sketch a diagram, you're going to label it, but it's also very important how you label it. You do want to label it intelligently. After reading the problem, you'll realize that you'll know what things are changing, what things are not changing. You always want to label things that are changing with variables. You always want to label things that are not changing with constants. Okay. 3, you're going to write down what you know and what you want to find. That's just to kind of keep you focused so you know what you're looking for at any given time. Because it's a long process, you don't want to get lost halfway through. Like, what should I be doing again? So I put in step 3 to make sure you're never lost, you know exactly where you're heading, you know exactly why you're doing what you're doing. 4, you're going to set up an equation. That's going to be the relationship, that how they're related, right? Now your equation is going to depend on the picture, right? So if your picture is a circle, you know you'll be thinking about like, oh, the equation is probably pi r squared, or it's probably this, or probably, you think about equations of a circle. If it's a rectangle, you think about equations that deal with a rectangle. If it's a triangle, you think about equations that deal with a triangle. Pick the relevant equation. That comes in step 4. In step 5, this is where the magic happens. You're going to differentiate. That's how you're going to figure out the rates of change, because the derivative is the rate of change. So you can figure out the rates of change by differentiating that equation. And finally, you reach to step 6. And that's going to be you solving for the rate that you want to find. So at step 6, hopefully all your unknowns, you know them except the one rate you want to find. You just plug it in and compute that rate. One hiccup that can happen here, and we'll go through an example where it does happen. Sometimes you'll get to step 6 and you won't have enough information. You might have variables missing, or there's a value that you don't know. Whenever that happens, you always go back to step 4. You'll always be able to find the missing data from step 4. So if you get to step 6 and you don't have enough information to figure things out, the missing pieces will be in step 4. Go back to step 4, figure out the information that's missing, then come back to step 6 and plug it in. And then at the end of this cycle, you should have the answer to the problem. So that's basically related rates. Read the problem carefully, draw and label a diagram, write what you know and what you want to find, set up an equation, differentiate it, plug in your knowns, solve for your unknown. That's the 6 steps. It will always be those 6 steps. Very rarely, and again, I don't think you guys will be in this situation, but in your homework you might have this situation. Very rarely you don't need to draw a diagram because they will literally give you the equation, right? So if they give you the equation for step 4, you can skip step 2. But usually they're going to describe something that they want you to actually draw something. That being said, I told you some things that you should know about at this point in this box. You're expected to know about the formulas for like perimeter, area of common 2-dimensional figures, circles, rectangles, triangles, etc. Remember volumes of very simple 3D figures like a cube or a box. You should know the volume is length times width times height. If it's a cylinder, you should know it's pi r squared times height, things of that sort. So there are some formulas that you're going to want to know because they like throwing geometry at you here. And with that said, that's pretty much the strategy. We're going to go through these problems. Not all of them, maybe. I mean, in my other classes this semester, I went through 3. And I think by the 3rd one, they were fine. So we'll do about 3 of them. And yeah, the first 3 will be good. You'll see the process 3 times. And the first 3, you'll see all the hiccups that could happen. You should be in good shape. But you should practice the rest and of course do your homework for extra practice. So let's actually jump into it. So we're going to do related rates. Let's do example 1 from the handout. So we're going to read the problem. That's always going to be step 1. So example 1, step 1 is to read A right circular cylinder undergoes expansion. Its radius is increasing at a rate of 1 meter per second, while its height is increasing at a rate of 2 meters per second. At what rate is the volume changing when the radius is 1 meter in length and the height is 3 meters? Okay, so this is an example of a related rates problem. Notice that they described to you a situation. Okay, we have a cylinder and it's expanding. They told you about how fast some things are moving. The radius is increasing at this speed, the height is increasing at that speed. And then they ask you how fast something else is moving. At what rate is the volume changing? Right? That's related rates. They describe a situation where you have a bunch of things with relationships. They tell you how fast some of them are moving, and they ask you how fast something else is moving. That's related rates, right there. Classic related rates problem. Okay, so after you read, second thing you're going to do is try to draw a diagram. They spoke about a right circular cylinder. This just means it's a circular cylinder where the axis is at a right angle to the base, so it's a very straight cylinder, it's not slanted. And of course, I would label this. Now we're told that both the height and the radius are changing, so I would label them with letters. This is R, call that H. Now, I wrote something in blue down here to tell you that the independent variable is always time. Meaning, when you see R and H, they're not just two variables. You want to think of them as functions. You want to think of them as functions of time. So this is an R, it's a function of time. R is just the name of the function. And this isn't just H, it's a function of time. Okay? T is the independent variable. Okay? So H, you want to think of a function. It's like an f of x or a y equals f of x, something like that. T is the independent variable. Okay? So that's the diagram. Okay? Now the point of drawing the diagram is to help you figure out the equation, right? So once you draw this picture, you should like be having flashbacks of high school geometry. You know, you go to your safe space and you're like, oh, I remember seeing that picture before. Oh, this is it. Okay. And there's an equation that went with it, right? Let's move to the third step. Now this is where you kind of set the intentions. It's going to be very important. At some point we're going to be plugging in a bunch of numbers. You want to have those numbers written down in one place very neatly. And so you don't have to, you don't want to be in the position where you're looking back at the word problem trying to figure out the numbers to plug them in, because that's possibilities for errors there. A lot of people look back into the word problem and take out the wrong number. So you read carefully and you pick out the things that you know so far and the thing that you want to find, and you're going to actually write that down. So we want to find a certain rate. What rates do we know? Well, we know how fast the radius is increasing. That's dr dt. Right? T is the independent variable. So the rate of change of r is its derivative, and I know that that is 1. The height is increasing at a rate of 2. That tells me that dh dt is 2. Okay, so that's what we know. Now here comes the question. At what rate is its volume changing? Which means what we want is dv dt. How fast is the volume moving? When the radius is 1 and the height is 3. So I want dv dt when r equals 1 and h equals 3. So that's the information I know. This is the information I want. Now, again, I'm going to just point some things out for emphasis here. I put these as positive numbers because they are increasing. Notice that in the problem, it said that the radius is increasing and the height is increasing, right? So it's very important that you read carefully, because if they said something like, oh, the radius is decreasing, you need to put a negative sign here. You'll get the wrong problem otherwise. You'll get the wrong answer otherwise. And of course, as a multiple choice, a lot of the answer choices, they're going to generate them by just putting the wrong sign where they expect students to not be paying attention. And you'll get the answer, it'll look like the right answer, but it only looks like the right answer because you made a wrong sign choice. So be careful, you're reading very carefully, you need to know when something's getting bigger or smaller. Increasing means the derivative is positive. So radius is increasing means the derivative is +1. Height is increasing at 2 means the derivative of h is +2. Now this brings us to step 4, which is going to be, we're going to set up that equation. So pretty much step 4 is, you're going to set up an equation that relates all the variables that you wrote down here, which are v, r, and h. What is the equation that relates all of those here? How can you talk about volume with the radius and height of a cylinder? Anyone remember? How do you find the volume of a cylinder?
R No, I don't know what I'm saying.
So it turns out for a cylinder, it's pi r squared h. So this is something that's called a prism from geometry class. I know I don't want to drag you back to those painful memories. But whenever you have a figure that it's pretty much the same shape, just being run along some axis, so you'll realize it's always the same circle. It's just being propagated along this axis. The axis passes through the center of all these circles, and you're just taking the circle and dragging it from one edge to the other, and you create this shape. The volume of such a thing is always going to be the area of the base times the height. Right? That's why the volume of a box is length times width times height, because the area of the base is length times width, and you multiply by the height. Right? So it's pi r squared, which is the area of the circle, times the height. So that's going to be the equation that we come up with here. And like I said, you should be practicing your very simple geometric formulas here. 5, we're going to differentiate. We're going to do it implicitly with respect to t. Remember, time is always our independent variable here. Our derivatives are in terms of t. So here the calculus comes in. How would I differentiate this equation with respect to time? What is the derivative of v?
So it's 2 pi.
What's the derivative of v?
Oh.
Huh?
I mean, 2 pi r.
V. What is the derivative of v?
Oh, v prime. That's not the whole equation.
Okay. Now what's the derivative of this side?
2
2
pi.
pi r. H prime. H prime.
2 pi h prime.
2 pi r.
Oh, wait.
Is there- isn't that
Multiply by both.
constant?
Oh, H
2 pi.
times H.
What is a constant?
The constant is the
R and h are functions of t.
Yeah, you gotta do the
So how can we differentiate this?
gotta do the
Product rule. So derivative rules still apply. They will always apply. Here we have a multiplication of functions here.
So
I have the function pi r squared. I have the function h. These are two functions being multiplied. In order to find the derivative, I need to do the product rule,
So
because
it's
it is
the
a
2
product
pi
of functions. So I'm going to differentiate this, leave that alone, plus differentiate this, leave that alone.
So
Okay.
it's 2 pi r h
So this one is 2 pi r h
plus pi r squared
times H prime.
times.
So
Times H prime.
So you said
times dh dt.
dh.
So you're missing something.
And then h prime. Wait.
This is h prime.
Oh, okay. You add back this.
Remember how the implicit differentiation works?
So you said
T is the independent variable.
So find the derivative of the first.
Also, you put
leave
t
it.
also
No.
with
Times the derivative.
Be more specific, where are you talking? Where?
Square.
Okay, so to remind you of implicit differentiation, you will go through and you will differentiate obeying all derivative rules. If you're differentiating the independent variable, you don't need to do anything. You just follow the derivative rules as written. If you're differentiating anything else, you have to multiply by its prime. That's the rule. If you differentiate anything that's not t, you have to multiply by the prime. What did you differentiate in this situation?
No.
everything but t. So you gotta multiply it by.
No, you only differentiated one thing at a time. What did you differentiate here?
I did.
R.
You differentiated the r, which means you should have done what?
R, the H.
Multiply by t.
Multiply by r prime. Once you differentiate the r, you have to multiply by dr dt. Then you read the h. This is implicit differentiation. If you're not the independent variable, you have to multiply by the prime every time you take a derivative, because it's the chain rule, right? Because when you see r squared, you have to remember, it's not just an r, it's a function, right? It means there's some function inside of a square, right? And so if you want to differentiate that with respect to time, you have to do the chain rule. The 2 has to come down in front, leave the inside alone, multiplied by the derivative of the inside. Right? So when I have to differentiate the r squared, it's 2r r prime for that reason. Right? It's implicit differentiation. Everything that's not a t, it's not just a letter, it's a function. You think of it as there's an inside function here. We just don't know what it is. You have to apply the chain rule. So the fifth step is not just differentiation, it is implicit differentiation, right? Meaning, if it's not a t, multiply by the prime every time you take a derivative of something. If you differentiate the r, you have to multiply by dr dt. Differentiate the h, you have to multiply by dh dt. Differentiate any letter other than t, you have to multiply by d that letter dt. So if there was a q, if I differentiate a q, I'd multiply by dq dt. Differentiate an L, multiply by dl dt. Differentiate an m, multiply by dm dt. Differentiate a t, don't do anything. That's implicit differentiation. Okay. So that is our derivative equation. Okay, so this was the original equation. Differentiating it, using the product rule and implicit differentiation gives me this. So now I realize what I actually want here. So let's actually write it down. So this happened because of the product rule. And these guys happened because of the chain rule. And now you have to remember, what is it that you're searching for, right? You probably forgot what we were talking about by now. We are talking about this guy. That's what we want, okay? Because that guy is right here. That's what we want.
What's the derivative?
So now in part 6, that's when we do that. In part 6, we're going to answer the question. In other words, we're going to plug in what we know, solve for what we want. Okay. Now if I want this guy, he's sitting nicely on one side of an equation, so let's not bother him. Let's plug in everyone over here to figure out what value we should have. And do I know everyone over there? Do I know what r is? Yes. Do I know what dr dt is? Yes. Do I know what h is? Yes. Do I know what dh dt is? Yes. I know everyone on this side. I can actually just plug in the numbers. So this means that dv dt is going to be equal to 2 pi times 1 times dr dt is again 1 times h,
3
3 plus pi times 1 squared times dh dt is 2. So this ends up being 6 pi plus 2 pi, and so that's 8 pi. If you want, it could be, this is volume, so feet cubed per second. Was it feet? Meters. So it's cubic meters per second. But 8 pi would be the answer. And this illustrates the related rates process. It's always going to be these 6 steps in this order. You're going to read the problem very carefully, figure out that it's a related rates. You also want to be able to pick up information with the correct sign. So you're going to read this carefully. Come up with a diagram that describes the situation. Label the diagram intelligently. Anything that's changing, label with letters. Anything that's not changing, label with numbers. Write down what you know, what you want to find. You're able to come up with an equation that relates all these variables. Once you have said equation, you will differentiate it with respect to time. All derivative rules apply. Product rule, quotient rule, chain rule, they all still work. You have to obey all these rules. Any letter that is not a t, it is not actually a letter, it is a function. You need to differentiate. Whenever you differentiate, you have to multiply by its derivative. Once you do that, you'll get to a situation where hopefully this equation is going to be enough to solve the problem. You'll be able to plug in all the stuff that you know from here to find the answer. And that's the problem. That's the related rates problem. Questions?
Yeah. Okay, so in step 5, you put like a dr over dt for like the derivative and everything, but where so don't do it how we usually do it, like the product rule and the prime and g and all that.
That's what we did here. We did that here.
So then why'd you plug in, why'd you put the 1 in that over there?
Because it is 1. dr dt is 1. R is 1 and dr dt is 1. So I plugged in a 1 here, plugged in a 1 here, plugged in a 3 here. With that. Because I have the information from. So everywhere I see dr dt, I can replace it with 1. If I see dh dt, I replace it with 2. If you see r, replace it with 1. If you see h, replace it with 2. So I'm just here, I'm literally plugging in everything I know and solving for what I don't know, which is the d. Let's do another example. Yeah, use this. So I'm going to erase these parts here. It is a template, you pretty much do the same thing, so I can even leave these labels up here. Related rates, we'll go through these 6 steps. Let's read the next problem. The length of the rectangle is increasing at a rate of 8 centimeters per second. Its width is increasing at a rate of 3 centimeters per second. When the length is 20 and the width is 10, how fast is the area increasing? Again, here's a situation they describe to you. They tell you how fast some things are changing. Width is increasing at 3, and the length is increasing at 8. And then they ask you how fast is the area changing. This is a related rates problem. So, you read the question. Now let's draw a diagram of the situation. They pretty much told us it was a rectangle, so I'm going to draw a rectangle. And now I am going to label the rectangle. How do you want to label this? What do you want this side to be? Huh?
With,
Come here?
like with, can I use a label?
Yeah, label. What do you want to label this?
The width?
Do you want to call that the width? What do you want to call this? H. Okay, so you can label it like that. It almost doesn't matter unless the question itself specifically tells you what to label stuff. Label it whatever you want. So now we can write down what do we know, what do we want. They told us the length. So I probably wouldn't use that because I probably wouldn't use H because they said length. You don't want your brain to have to go through some extra translation. So let's use L. Doesn't matter, but it's going to confuse you. They use width and length. So let's keep it as width and length. They told us that the length is increasing at 8. How can I write down that information? Saying the length is increasing at 8. What is, how can I say that? dr? There's no R here.
Oh, wait.
That is saying dl
Yeah, DL.
over dt is 8. They told me the width is increasing at 3. What does that say?
So DW over DT equals 3.
Okay, now they said, find how fast the area is increasing. So that means we want to find the rate of change of area in a specific instance. So they'll tell you what they wanted, they'll tell you when they want it. They said when the length is 20, when L is 20, and the width is 10. And at this point you can forget about looking at the problem again because we have all the information we would need here. Okay. So we read it, we have a rectangle, the length is increasing at 8 centimeters per second, the width is increasing at 3. We want to find how fast is the area increasing when the length is 20 and the width is 10. What equation can I come up with that will relate A, L, and W? Right, which is?
Nice times with times sign.
What? It's asking about the area of a rectangle. What's the formula for the area of a rectangle?
What?
Right, it's going to be W times L. So that's the equation. That's the area of a rectangle. Now you have the equation, you're going to differentiate this equation. What's the derivative of the A? It's just A prime, the ADT. How do I differentiate this side?
So is this the product rule too?
It's the product rule because I have two functions multiplying each other. I have a W multiplying an L.
So it's 1 times
That's what?
1.
So isn't it 1
1 times W.
1 times what?
DL over D8 DT? Sorry.
1 dl over dt. Continue, I'm waiting on you guys.
L?
Wait, so where do you get the
Plus,
derivative of x of dw over dt, times 1. No?
no, that's totally wrong. What does the product rule say? What does the product rule say we should do?
Wait, isn't
Prime
it?
times,
I mean, you guys write this on quizzes, right? So if you want to, you have something multiplying, you want to differentiate it, what does the rule say you should do?
So that's times the derivative of g of x plus g of x times the derivative of x.
Order is kind of weird there, but it's fine in the product rule. The quotient rule, the order is very specific. I probably memorized the order in that way.
so
So it gives you, it's the same thing, but I'd rather do it this way. Why? Because if I memorize the quotient rule, now I just change the middle sign, and I'm good.
so f
So,
prime.
in other words, you differentiate one thing, leave the other one alone. Don't do anything. Plus, leave the first thing alone, differentiate the second thing. This is the product rule. Okay. What is the derivative of this?
So it'll be one times
Come again?
1 times don't.
1 times?
L.
Plus W. Now starting with 3
It's a little better, but that's still wrong.
Because it's not, like, you have to do the chain rule, right?
And then
Right. It's implicit differentiation,
is
which
it?
means if you differentiated the W, what do you need to do?
You have to do them wrong.
You have to multiply by dW dt. If you differentiated the L, what do you need to do? You have to multiply by dL dt. You cannot forget the chain rules. These are not letters, these are functions. Time is the independent variable. Time is always the independent variable. That's the only guy that when you differentiate, you don't have to do anything.
So,
Every time you're differentiating anyone else, any other letter other than T itself, you have to multiply by the derivative whenever you differentiate that thing.
what?
That's the derivative equation.
Wow.
Okay, now, we move on to step 6. Now step 6 says what? Plug in what we know, solve for what we want. What do we want?
When L equals 20 and W equals 10.
What?
Plug in.
That's what we want, right?
We want when L equals 20 and W equals 10.
No, that's what we have.
You want the area one.
Oh.
I want the rate of change of area when L equals 20 and W equals 10. That's like you asked me, what do I want? And I said, oh, when it's past noon. Like I didn't answer the question.
So when
No,
you,
I want this guy. When in this situation. So I want this guy. That's what I'm looking for. That's what's important.
so when you.
When do I want that? When these values are in effect.
So what you do, so since dw over dt equals to 3, you plug in 3
Yep.
times 20
dw dt from here is 3. So I'm going to plug in 3 here.
times 20
Times L, which is 20.
plus 10 times dl dt, which is 8.
So now this is 60 plus 80, that's 140. And I think this was in centimeters. So area is squared, units, centimeters squared. So to go through the process again, read the problem very carefully. You have to recognize that it's a related rates problem and be able to pick out the important information. Draw a diagram of the situation, label it very carefully, things that are changing, label variables. Remember that these variables are functions of time. Time is the independent variable. They are not their own letters. Then, write down what you know, what you want to find, and come up with an equation that relates all the variables here. And then you're going to differentiate that. You must remember it's an implicit differentiation. Time is always the independent variable. If you differentiate anyone other than t, you must multiply by the derivative. Other than that, you're following the same derivative rules, product rule, quotient rule, chain rule, they all still apply. It's just that whenever you differentiate something, multiply by the prime. Then you're going to plug in what you know, solve for what you want. And by the time you get there, that should be the answer. Okay, let's run through it again. That was example 2. Let's look at example 3. Okay, so here's the question. A 15-foot ladder is resting against a vertical wall. Suddenly, and without warning, the foot of the ladder begins to slide away from the wall at a rate of 2 feet per second. at what rate is the top of the ladder sliding down the wall when the foot of the ladder is 9 feet from the wall? That's the question. So, what? There's a ladder and the wall, what's going on? Well, you should recognize it's a related rates problem. They told you how fast something was happening, and then they asked you how fast something else is happening. They said the foot is sliding away at 2 feet per second. How fast is this thing sliding down? That should tell you, okay, related rates. So now you get your bearings, you know you're going to go through these 6 steps. Then you read carefully because now you're going to want to pick out the important information. Now, so you have a ladder leaning against the vertical wall. It's a 15-foot ladder. How can you represent that in a picture? Huh? The picture, what would the picture?
Oh, like.
It's a triangle, it's a right triangle,
Right triangle.
right? So you have a vertical wall, you have a ladder leaning against it, and you have the ground, which is what it's standing on, right? That's a triangle screaming out at you. Okay, so the correct diagram here is a triangle. In fact, it's a right triangle. Now, how would you label this triangle? What do you want to label this? Huh? What?
Base, the base?
So you'd write out base?
No.
What would you label it? B. Okay. What about here? Okay, sounds like fine. What about here?
C.
A, B, C. Makes sense. I wouldn't label the diagram this way. Why not? So in the steps, and again, I suggest you read this handout very carefully. So it says, draw a diagram, label the quantities that are changing with variables and the quantities that are not changing with constants. So because of that sentence, I would not label the triangle this way.
Because like the constant thing?
What's constant?
Well, like the C would be confusing, like why does it matter?
Huh?
Why wouldn't you label it like that? Well, like what would you?
This is representing the ladder, right?
Yeah.
Is the length of the ladder changing?
Oh, no, it's 15.
It's not. Therefore, I would not label it with a variable. I would label it with the constant value. I would label that 15, specifically 15. It is not something that's moving. The ladder is always going to be 15 feet. It's not going to change length during this problem. That is the correct kind of labeling. Okay. So, that's my diagram after reading this situation. Okay, now, what do we know? What do we want? Well, we know that the foot of the ladder is sliding away from the wall at 2 feet per second. So this guy's sliding away that way, right? Now what you have to realize, what that means is that the length D, is it getting bigger or smaller? It's getting larger because the foot is sliding away. So B is getting larger. So I know my dB dt is plus something. Plus what?
Plus 2.
Plus 2. The foot of the ladder is sliding away from the wall. This means this on this picture, the B is getting bigger. This means it's increasing, which means I put a plus 2. If the question was phrased, oh, the foot of the ladder is being pushed towards the wall, you would put a minus 2. This would change. Okay, so I want you to, like, these things, they matter, right? And they'll catch you. So, like on a final, they put, oh, the foot of the ladder is being pushed towards the wall, and then they'll work out an answer where there's a plus here, but it really should be a minus, and you're going to pick the wrong answer, right? B is increasing, right? In this scenario, the B is getting larger. Okay. By the way, what do you expect to happen to A?
It gets smaller.
It'll get smaller. So if you were to talk about the rate of A, what would you think the value should be?
It should be minus.
It should be negative something, right? Which means at the end of the day, I am going to get dA dt. It must be negative something, right? Now if I'm working on my answer and I don't get a negative number, I know I made a mistake somewhere. It has to be negative. Okay. So So all of that you get just from reading the problem. You want to understand the situation. What's getting bigger? What's getting smaller? What should the signs be? How are these numbers supposed to behave? Okay. So, and that's all they told me. And then they asked, at what rate is the top of the ladder sliding down? So they pretty much want to know how fast is this happening. So what we want is dA dt. When, so now you want to find the situation. When the foot of the ladder is 9 feet from the wall, how would I express that?
When 90 feet from the wall?
9 feet from the wall.
So,
How would I express that?
so it's A is the wall.
A is literally the wall, so the ladder is touching the wall. I want to know where the foot of the ladder is 9 feet from the wall. Where
So is that minus?
B equals 9.
It means B equals 9. B measures the distance from the foot of the ladder is from the wall. Saying that the foot of the ladder is 9 feet from the wall is them telling me B equals 9. What equation would you set up here?
So
A squared plus B squared is C squared?
Right, this is Pythagoras' theorem, right? Classic case. We have a right triangle where we know all the side lengths, so Pythagoras' theorem should be an equation that's jumping out at you. We would know here that A squared plus B squared is equal to 15 squared. Sum of the squares of the two legs is the square of the hypotenuse. That's Pythagoras' theorem. Okay, so that's the equation that describes this situation. Now we're going to differentiate this equation implicitly with respect to time. Okay, so what is the derivative of A squared?
So it's dA over dt times 2A.
Okay, that's kind of backwards, but 2A dA dt, sure.
Okay.
Derivative of B squared.
Plus 2B dB dt equals to 30. Then just seems
What's the derivative of 15 squared?
2.
it's just
Or
0.
It's a constant.
It's 0. It's a constant. It's a constant. Derivative of constant is 0 all the time. It's always been that way. Okay. Now, this is one of the reasons, I mean, if a constant being squared is confusing, you can imagine what would have happened had you put a C here. How much more confused you would have been about the situation. Because here you're going to have a C squared. You're differentiating that, you've got 2C times dC dt. Now you're going to wonder, what is dC dt? Where the question is incomplete, or no, this professor sucks, he wrote the wrong problem. No, you made the problem complicated by throwing in letters that you didn't need. So now it's like you have extra information, you're going to be confused, you're going to think, isn't this missing something? It's not missing anything. You just labeled something a variable that you shouldn't have. Okay? That's why labeling is important, because now you just know there's really only 2 variables I should be worried about, not 3. Right? And then you'd also know the derivative of a constant is 0. Like you see 15 squared, it's a number. 0 is the derivative. So that's the derivative equation. In fact, I can kind of divide both sides by 2 here. So that's A dA dt plus B dt equals 0. Now we're going to say, now we ask the question, what do we want?
We want dA dt when B.
We want dA dt. So this is the guy I care about in this equation, which means I want to be able to plug in the values for everyone else and solve for that guy.
But
Right?
we can't
So this
find
means
AB.
dA dt is, I can bring this over, this minus b times dB dt, divided by,
A.
I can divide that by a. And so now all I'm going to do is I'm going to plug in these numbers.
So what's A?
What's A? Oh wow, she already saw, there's a problem. What the heck is this? So here we got to step 6 and there's some missing information. I have an equation and I have two unknowns. What do we do when we get to step 6 and we're missing information?
So would you, clean,
Go back to 4.
would
You go back to step 4. So that's why I tell you, sometimes when you get to step 6, you'll be missing information. Whenever this happens, go back to step 4. Right? When you read in the handout, that's what it's going to say. So if you get here and you realize, oh, I don't have enough information to solve for what I want, go back to step 4. Step 4 is going to be where you find that information. So I need to find A, I only know B. So what I can do is I can go to this equation, plug in the B, and solve for the A. Okay? So here, back to 4. Now you're going to go back to 4 and you're going to solve that equation. So you know that A squared plus B squared, which is 9 squared, equals 15 squared. This means that A is equal to what? Something you should, no. Something you should be able to answer very quickly.
144,
Because
so
there's a
12.
pattern here.
12.
Huh?
It's 12 square.
It's 12, right? Did you actually use a calculator? Use a calculator, you can use a calculator. It is 12. You could kind of know this without a calculator though. Of course, I mean, if you don't see the pattern, then by all means,
I
just
don't.
do your calculator. You'd have to find 15 squared, subtract 9 squared, and then take the square root of that. If you're not in the calculator section, that might cause you a little bit of extra time. What you could realize is that it's a 3, 4, 5 triangle. Right? So notice that you have a triangle where you know one side is 15 and the other side is 9, and you want to find this side. Okay? Now there's a very common type of right triangle that you're very commonly tested on. It's called a 3, 4, 5. It says in a right triangle, if the hypotenuse is 5 and one side is 3, the other side must be 4, and vice versa. Right? The numbers 3, 4, and 5 go together in a right triangle. If you know the legs are 3 and 4 respectively, the hypotenuse must be 5. If you know the hypotenuse is 5, one side is 3, the other side must be 4. You know the hypotenuse is 5, one side is 4, the other side must be 3. These numbers always go together. They're called Pythagorean triples. And this is called a 3, 4, 5 triangle. Right? It would have been something that was emphasized in high school. They'll expect you to remember these things for some odd reason. But it's a 3, 4, 5 triangle. Now what that allows you to do is it allows you to make calculations a lot quickly, a lot more quickly in the non-calculator section. The thing is, this relationship is maintained under proportion. So if I multiply all the numbers by the same number, it still works for the right triangle. So in other words, you'll realize to get 15, I had to multiply this by 3. To get 9, I multiplied this by 3. So what would the other leg be? Well, it'll be 4 by 3. It's going to be 12. Right? So it's a very common number pattern to show up with right triangles. Yet you also have some other ones like in 5, 7, 13. But 3, 4, 5 is a common pattern, right? So if they're throwing a right triangle at you, you should look out for patterns like that. There are two sets of numbers. 3, 4, 5 is by far more common though. Ultimately though, the point is, you're missing information here, go back to step 4, solve for it. Here we realize that A is 12, and so now we can actually continue the problem.
It's negative 18.
So we would have, this is equal to
Negative
minus B
times
dB
2
dt
over 12.
over 12.
It's negative
And then 2
18
to
over
this
12.
goes 6, 2 to that goes.
9.
So it's minus 3 over 2. And so now we make sense. We actually predicted that the answer would be minus. So now we know that, yeah, we have reason to be confident in our answer here. So minus 3 over 2 would be the answer. And this is in feet per second. Although you don't have to know the units, the answer choices will have the units with them. And I don't think they make all the answer choices the same, but change the units on you. Units is a really big thing they test you on.
They changed the number.
They'll change the numbers. And they'll change it in such a way like you might see a positive 3 over 2.
see.
Or they-
Thirds.
Or they'll try to guess, oh, maybe they'll guess this was 6, and they would put it in there. Or maybe they put a -2 somewhere, and they'll generate answers that will go through some common mistakes. They'd also put a mistake where students will actually try to differentiate this and put 2 times 15 and put 30 here. And then they're gonna create an answer with 30 on that side of the equation, and that's gonna be one of the answer choices. Because for some reason, once you're doing something moderately sophisticated, students forget the very basics. Derivative of a constant is 0 for any constant. So things like that will happen. Okay. I think we'll stop there. Sean is yawning for a little break. But good news, we just finished the calculus portion. This is all we're doing for calculus. So the rest of it is going to be matrices, which students tend to have a better time
When
with.
do we have the mock, the final?
It'll be closer to the final.
I want to try it.
You're not ready to try it. You'll try it when you know.